Hello everyone, here's our group chosen paper's title. And this paper explores how reinforcement learning can help LLM models interact with the real environments more effectively and make better decisions. And now let's start from the background.
Before introducing the paper, it is important to understand the concept of embodied AI. Embodied AI focuses on agents that interact with environments, observe states, make decisions, and perform actions to achieve goals. As shown in the examples on the left, agents operate in virtual household environments and complete tasks such as food preparation and entertainment activities. Large language models provide strong reasoning and language understanding capabilities, making them promising decision-making agents for embodied environments. Embodied agents have many potential applications in the real world. As shown in these examples, agents can perform household tasks such as food preparation and entertainment activities in virtual environments. Similar technologies can be applied to serve robots, smart assistants, and human AI collaboration systems. To succeed in these tasks, make decisions and interact effectively with their environments. This is why combining large language models with embodied environments has become an important research direction. Now let's turn to Jiaxuan to introduce the part of motivation.
The motivation of this paper comes from a key contradiction between large language models and reinforcement learning. LLM has strong prior knowledge. They can understand instructions, reason about tasks, and give reasonable action suggestions. However, when they are placed in embodied environments, their knowledge may not match the actual rules of the environment. For example, in a cooking task, the model may suggest using pepper, even though these ingredients do not exist in the environment. It may also misunderstand the environment constraints, such as trying to put two ingredients on the same cutting board, although the environment only allows one item at a time. So this means the problem is not that LLM has no knowledge, but their knowledge is not grounded in the specific environment. They rely on general common sense, and while decision-making tasks require accurate understanding of the valid actions and the state transitions. On the other hand, RL agents can learn directly from the environment feedback. Through try and error, they can eventually align their behavior with the environment. However, traditional RL usually start from a random policy, so it is inefficient, especially in tasks with large action space, long horizons, or spread reports. Therefore, the motivation of this paper is to combine the strengths of both sides. LLMs provide the useful prior knowledge for better exploration, and IL use real environment reports to correct the wrong assumptions. In this way, the agent can both benefit from language knowledge and gradually become aligned with the embodied environment.
Okay, thanks, Joshua. Let's look at the challenges using AI in robots has two big programs. First, AI often makes bad choices that do not exist in the world. Second, AI does not know cutting rules. For example, it may try to put too many things on a cutting board because it thinks is okay. Traditional training can fix this, but it's very slow at the start. Our new framework fixes this by combining AI technology with step-by-step training. However, giving AI a list of choices introduces a lens base. In condition 1, the total score of an action comes from multiplying token scores. Because each score is less than 1, longer actions are always punished. For example, the bad choice pick up the tomatoes have 5 tokens, but a bad shortcut like serve the dash has only 4. This mathematical bias makes the training very unstable. To check our solutions, token normalization is too stronger and hurts data efficiency. Instead, our word normalization fixes this by counting words instead of letters, making the model very stable. But we must admit two limitations. First, the system is too sensitive to grammar. If you lose a simple word like the, the, AI score drops sharply. Second, the computer cost is too high. Testing every real action test through the big AI model and every step slows down our training speed, which is our main problem for the future. Thank you.
Hello, my name is Chen Lipian. Now let me walk you through the core methodology of TwoSum. The key idea of TwoSum is to convert an LLM into a valid policy without generating free-form actions. Instead of asking the LLM to output an action directly, TwoSum evaluates the likelihood of every valid action in the environmental. For each action, it combines the observation per mode with an action per mode. computes a joint token probability, and then applies softmax across all actions to obtain a behavior policy. This guarantees the syntax an action is always valid and allows the framework to work with an action that can be experienced in natural language. The next part is the action promo normalization. A challenge is that longer action promos mutually receive lower probability because they contains more tokens. Two-sum addresses this with a normalization. Token normalization average log probability across tokens, but it can overcorrect because tokens with the same word are highly dependent. Word normalization is set average by the number of words, since LLMs often predict later tokens of a word with very high confidence once the first token appears. Word-level normalization better reflects the linguistic structure experiment and show it provides faster convergence and more stable training. The last part of the methodology is the PPO training and the promo design. For training, two-sum is a frozen LMMA 7B model with an LoRa adapters, updating only a small numbers of parameters. A lightweight MLP serves as a critical, and the PPO is applied with an KL divergence construct. The framework also follows for promotes design principles, main observation action flow, preserving articles, repeating key lengths, and using context-aware phrasing. The resulting of LoRa model is lightweight, transform across environmentals, and preserve the LMS original language capability.
My name is Shang Yuchen, AIT306 Right, let's move on to the core of our research, the dataset. Actually, in our study, calling it a dataset is a bit of understatement. It's more like a massive evolving library of adversarial attacks. Think about how we usually test AI safety. We usually hire human experts to write tricky questions, but here's the problem. Humans are expensive, and we get tired. When we are tired, we aren't that creative. We repeat the same patterns. This leaves huge blind spots where the AI hasn't been tested, so we realized we needed a more dynamic approach. So, how did we build our data? We used curiosity-driven red teaming. We basically trained one AI, the tech LLM, to find weakness in other AI like LLMA 2, but the secret source is the curiosity reward. Normally, an AI gets lazy. If it finds one trick that works, it just keeps doing it. We fix that. Our system gives the AI a bonus for trying something new and different. If a promote is too similar to what it tried before, it gets a lower score. This forces the model to be truly original. The result? We generated over 100,000 unique test cases, and these aren't just random sentences. They are diverse, high-quality attacks that cover a huge range of risks, from subtle toxicity to complex bias. Because of this scale and the diversity, we can say our dataset provides a true stress test for modern language models. Next, let's see how we used this data to improve model robustness.
Hi, here's Lishi, and let's see the experimental result comparison with the baselines. This figure we can see is compared to two-sum with PPO and prose-only methods across 4 tasks: tomato salad, tomato lettuce salad, food preparation, and entertainment. We can see that the two-sum consistently achieves higher returns and converges much faster than the baselines. In the more challenging tomato lettuce salad task, PPO requires over 500,000 training steps, while the two-sum reaches nearly optimal performance within about 80,000 steps. And CPD improvements are observed in virtual home, where the two-sum handles large action space more effectively. And this result can show that the combining LLM prior knowledge with the reinforcement learning significantly improves the learning efficiency and the task performance. Then let's see, why does the two-sum work? This shows the effects of the word normalization. Compared with token normalization and no normalization, word normalization provides the most stable training and the fastest convergency. It also avoids bias towards shorter action promotes, leading to a better action selection. Therefore, model normalization is a key factor behind the stronger performance of two-sum. Here's the conclusion. In summary, two-sum combines the latency of the LLMs and reinforcement learning. It achieves better performance, faster learning, and stronger generalization. Overall, it provides a promising direction for future embodied AI systems. Okay, that's all. Thank you.